Chapter 5 today. This is Vodcast number 15, and we're going to cover section 5.1, which is the continuity equation, which is a way of expressing the conservation of mass. So the first thing that I'd like to talk about is how we're going to approach Chapter 5. Chapter 5 is an approach of fluid dynamics, which is referred to as finite control volume analysis. And in your textbook, what you'll see is that when we talk about a control volume, what we're really talking about is a fixed or a volume in space. The volume can be moving, it can be deformable, it can be undeformable, or it can be relative to something else. But we're not talking about a fixed mass. So what we're really doing in terms of Chapter 5, when we talk about a finite control volume analysis, we are using the ideas of conservation of mass as mass or a system moves through a control volume, a place in space. Whether the place is stationary, whether it's moving, whether it remains the same size or not. So in Chapter 4, we discussed the idea that a system is a collection of particular particles or a particular slug of a mass of a fluid, and that a control volume is the space they occupy at a particular time. Okay, so we can have any sort of a control volume, a balloon, for example, and the boundary of that balloon would be the control surface. The mass inside is equal to the system, and the balloon itself is the control volume. Now, if we allow air to be released from that balloon, the control surface is different, the control volume is different, and the system is the mass that has been released and the mass that remains inside of the control volume. Now, a balloon is a particularly good example because there's a couple of different things. First of all, it's deforming. Second of all, the mass or the system and the control volume at the beginning are exactly the same, and then later some of the mass is left, so the system and the control volume are no longer in the same location. And then also, in addition to the control volume deforming, it may be moving. If the air is allowed to squirt out of the balloon, that will actually propel the balloon to move forward. So we have a lot of different things going on with this relatively simple way of looking at a control volume. Now, just a second, I was trying to get this, there we go, that's a little bit better. I was just moving around on the PC trying to get this the textbook to look a little bit bigger. All right, so what we have here, we're going to reduce this pretty quickly to a fairly simple set of equations. But basically, after we go through this little derivation, what we can see, if I can get rid of that, what we can see here is that we have the time rate of change of rho v of the control volume plus the rho VNDA going through the control system, through the control surface is equal to 0. So this is the time rate of change of the mass within the control volume, and this is what's leaving the control volume. So basically what this says is that mass is conserved. What remains, what's changing rather, within the control volume, plus what passes the boundaries of the control volume, remains the same in terms of mass. And if you notice, rho times V, rho times volume, is a mass term, and V times A is a mass flow, or is a volumetric flow rate term, multiplied by density is a mass flow rate term. So each of these terms is mass flow rate. So the continuity equation is a statement that mass is conserved. So I'm just going to put this up on the document cam. And basically we're going to say the continuity equation is an expression for a control volume that mass is conserved. So section 5.1 talks about this and spends some time showing you that these statements can be derived or can be shown to be equivalent to the material balance equation. But basically, in terms of solving these problems, there are just a couple of things that we need to know. And the execution of these problems is not terribly difficult if you keep the basic premise in mind that mass is conserved. So let's take a look at this from a functional point of view and say, if we take the mass in the control volume at time 1, and we add to that the mass that enters or goes into the control volume over some period of time, and we subtract from that the mass that exits the control volume over that same period of time, that we will get the mass in the control volume at time 2. And if we rearrange this equation a little bit, we can say we have a delta mCv, because the mass in the control volume at time 2 minus the mass in the control volume at time 1 is a delta mCv. And if we then take the first time derivative of this expression, we can say that the rate at which mass enters the control volume minus the rate at which mass exits the control volume is equal to the rate of change of mass within the control volume with respect to time. And that's necessary for conservation of mass to occur. So let's break down a couple of these terms and start with this, which is sort of one of the more important ones. Mass flow rate, which is in kilograms per second, is going to be equal to the density of a fluid times the volumetric flow rate. And the volumetric flow rate is going to be equal to the area through which it flows times the velocity that is perpendicular to that area. So that's really that A dot, the V dot N term, okay? So you can see then that M dot, if we integrate over this area, looks like this. And that is actually equivalent to the expression that we got when we talked about the material balance or the Reynolds transport theorem. So if we decide, or if we declare or define V bar as being the average velocity of the fluid, we can say that V bar is equal to that term over the density times the area, and that in that way we can also just say that that's equal to the velocity for one-dimensional flow. So your textbook then breaks down some examples. If you have a steady flow, let's go ahead and write this out. if we have this expression, this comes from Reynolds transport. Okay, good expression for the continuity equation. If you have steady flow, the ddt properties are equal to 0. So, in other words, we would just have that, the integration over control surface, there we go, the control surface is equal to 0. What this really is telling us is that if there's no time rate of change of mass within the control volume, that what passes the control surface, in other words, what goes in and goes out, has to equal each other. And we can further reduce this if we just have a single inlet and a single outlet to say m dot 2 or out minus m dot 1 or in is equal to 0. Now also we know that m dot is equal to rho times q, where q is the volumetric flow rate. So we could say that rho 2 or rho out times q out equals rho 1 times q1. And I would prefer using out and in, but your authors use 1 and 2, so I'm trying to be consistent with how your authors write this. And then if the fluid is incompressible, that means that rho 2 is equal to rho 1, and therefore q2 is equal to q1. Or volumetric flow rates are also conserved only in the case that the fluid is incompressible. If the fluid's compressible, we have to take into account the density because in general, volume and volumetric flow rate is not conserved. So your authors go through some interesting expressions for control, for deforming control volumes, for moving control volumes, and it always comes back to these same ideas, that the mass is conserved. If you have a change of mass in the control volume, you need to account for it going in and out, and if there is no change of mass within the control volume, then, in other words, if it's steady flow, then the mass flow rates out will have to equal the mass flow rates in. So I'm going to solve or work for you two problems. I'm going to work out problem 5.1 in your textbook, and we'll turn to page 5. We'll turn to the page that problem is on. And after I do 5.1, 5.1 is relatively straightforward. After I finish 5.1, then I will do 5.25 so that you can see a couple of different types of ways that we can apply the continuity equation. All right, so the homework for this chapter begins on page 278. And problem 5.1 is actually a problem with water flowing into a sink. So basically, we have a faucet, and we have a flow rate, volumetric flow rate, of 2 gallons per minute emptying into a sink. All right? And it says determine the average velocity through each of the 3.4-inch diameter overflow holes if the drain is closed. Okay, so this drain is closed, so that means m dot out has to be equal to 0 here, correct? But it says we have 3 overflows. So like you might have this little, might see sometimes in a sink, you'll have a hole and there will be some tubes attached to it in some way is what they're saying in this case. And there are actually 3 of those, and each of those has a diameter of 0.4 inches, and there are 3 of those overflows. All right, so going back to the document CAM, this is sort of my representation. We have the faucet where we're getting 2 gallons per minute, and we have 3 overflows. So what are we basically saying? If the water level in the sink remains constant, that means that the volume in the sink is constant, and that V dot, which we've said is Q, well, it's not really a Q, it's a dVcd dt, is equal to 0, because if the volume is constant, the rate of change of volume in the sink is equal to 0. So if we call the sink our control volume, we can then say that the mass flow rate in minus the mass flow rate out is equal to 0, because dmCv dt is equal to 0. All right, so we have one flow rate in. Q in is 2 gallons per minute. So that must mean that Q out is also 2 gallons per minute. And what does that tell us? We are looking for the velocity through each of the drains. Well, we know that there are 3 drains, and we know that each one of them has a diameter of 0.4 inches. All right. Well, Q per drain then, since there are 3 of them and they have equal diameters, we can say that it's going to equal the Q in divided by 3, which is 2 gallons per minute divided by 3, or 2/3 gallon per minute. Now, a gallon per minute is kind of a strange unit to work with. But let's say if we want to get that into cubic feet per second, we can find that each drain has 2/3 of a gallon per minute. And if you look up the properties of water, you'll see that there is the density of water is, or excuse me, not the density of water, excuse me. There are approximately 7.5 gallons per cubic feet. And you could find that conversion factor in your textbook or online, but a volume, gallons per minute, to feet per second, we don't really have that specified in the back of your textbook, but there are, I guess the best way to put it is that there are approximately 7.5 gallons is the same as 1 cubic foot. Okay, so where could we look that up? Well, we could, for example, look it up on conversion factors on Google. Let's say conversion cubic to gallons, right? And so you get that 1 cubic foot is the same as 7.48 cubic gallons. So I'll use 7.48 instead of 7.5 in my conversion. Okay, so we'll just say 7.48. All right, so if we have 2/3 gallons per minute and we have 7.48 gallons per cubic foot, and we have 1 minute per 60 seconds, we can convert our gallons per minute to cubic feet per second per drain, because I've divided this by 3, and I get 2 divided by 3 divided again by 7.48 and divided again by 60. And so the value that I get per drain is 0.00 0.1485. It's an awful lot of significant figures, but we'll keep it there for a little bit. Cubic feet per second. And the question is, what is the average velocity? Well, we know that velocity times area is equal to volumetric flow rate. So that must mean that the velocity is equal to the volumetric flow rate divided by the area. We just found the volumetric flow rate in cubic feet per second. And we know that these are basically circular, these tubes. So 0.4 inches as a diameter. We know that the area is pi d squared over 4 for a circle. So assuming that it's a circle, we can put this over the area. Pi times d, 0.4 inches, times 12 inches per foot. I get my units consistent. Divided by 4, which in the numerator, the denominator of the denominator flips to the numerator. And so I get an average velocity, d squared. There we go. So I have feet squared canceling feet cubed to feet and seconds. So my units here will be feet per second. So let's see what my number turns out to be. 0.001485 times 4 divided by pi and divided again by 0.4 squared and then multiplied by 144, because 12 times 12 in the denominator flips up to the top, and I get 1.7 feet per second. All right, so what that tells me then for problem 5.1 is if the level in the sink remains the same, that all of the water that's going in has to come out of these drain tubes. So I can just take the volume of water that goes in, and once I feel safe making the assumption that the density of water remains the same, that it is incompressible, then I can make the leap that all of the water is coming out, and I can just change my units to a velocity based on the fact that that area is a circle. All right. So the next problem I'd like to work is a similar problem, but it's with a deformable control volume, and so it's a little bit more complicated. I wouldn't say it's really tricky, but we need to think our way through a couple more things when we do this problem. The problem I'd like to do is 5.25, where we have a hypodermic syringe, and it's used to apply a vaccine. The plunger is moved forward at a steady rate of 20 millimeters per second. That looks like a velocity, doesn't it? And the vaccine leaks past the plunger at 0.1 of the volumetric flow rate out the needle opening. So what we really have here is the vaccine exiting in two different places. We have a volumetric flow rate out of the needle, and we also have a volumetric flow rate of a leak, and then we have a deformable control volume. As we push the plunger in, the control volume gets smaller. All right, so the picture I've drawn looks like this. So we have some Q coming out here, we have some Q coming out here, and that's equal to 0.1 times the Q out on the needle, and then we're pushing here. So what's going on in the control volume? We are losing mass in the control volume this time, aren't we? All right, so if we are losing mass in the control volume, we have to take that into account. So the change of mass, density times this differential volume in the control volume. Let me write this out here. This is the change in mass in the control volume. And it's a little easier to express it in terms of volume because we are changing volume. In other words, the volume itself is changing as we push the plunger in. The density, we're going to assume that the vaccine is incompressible. And if it's a fluid, that's a pretty good assumption. Okay, so we can pull rho out of this. Okay, so all we're really looking at then is what the change is in terms of the volume. So let's call the distance that we move the plunger over this amount of time L. And if we do that, then we can say that the length times the area of the plunger plus the volume of the needle is going to be that change in the control volume. And of course we have to multiply the whole thing by rho. And this isn't really an integral anymore. I've already done that because it's really discrete. So we can call this the volume squeezed out. Okay. Then let's take a look at what's going on at the time rate of change. Let's call this equation 1. So for our next equation, we know that the time rate of change in the control volume of this is going to equal rho times A. This is volume. Let's call this dl dt. Because if this is the length, the dl dt is actually the velocity, isn't it? So let's just make a note of that, where dl dt is equal to minus the volume in the or the velocity of the plunger. Okay, and let's call that equation 2. All right. Well, if we combine these ideas, then we can say minus rho AV of the plunger plus m dot in the needle, which is rho times Q of the needle, plus m dot of the leak, which is rho Q of the leak. Those three things added together equals 0. All right, so this is what's going on in the control volume. This is what's coming back out of the syringe, either through the needle or through the leak. All right, well, we've decided that it's incompressible, so since rho is constant, it actually factors out of all of those terms. We can say minus AVP equals Q needle. I'm sorry, if I do that, I'm going to bring this over to the other side as a positive. So I get AVP is equal to Q needle plus Q leak. And we're told that Q leak is 1/10 or 0.1 times this. So you can say Q needle plus 0.1 Q needle. And algebraically, we can see that that's just 1 plus 1.1 plus 0.1, or 1.1 times the Q of the needle. Right, so we get the area times the V of the plunger is equal to that. All right, so continue with that idea then. What are we looking for? We're looking for the velocity of the needle. Okay, well, this is the area of the needle times velocity of the needle, right? So if we wish to solve this for the velocity of the needle, we can say the area of the plunger times velocity of the plunger divided by 1.1 times the area of the needle is equal to velocity of the needle. And we know that both of these are relatively circular, so we can say the area of the plunger is equal to pi times the diameter of the plunger squared over 4, and the area of the needle is equal to A times the diameter of the needle squared over 4. And if I take A p and divide it by an, these cancel and these cancel, so that's equal to d sub p squared over d sub n squared. So algebraically, we're kind of getting somewhere, aren't we? So we get dp squared over dn squared times vp over 1.1 is equal to vn. We're told that the inside diameters of the syringe and the needle are 20 millimeters and 0.7 millimeters. So we can put 20 squared over 0.7 squared for this term. And even though it's in millimeters, it doesn't matter because they cancel each other out. Then we have the velocity of the plunger, which we're told is 20 millimeters per second, and then over 1.1. These units will cancel out, and we'll be left with this value of v sub n in millimeters per second. So let's see what that looks like. 20 squared divided by 0.7 squared times 20 divided by 1.1. And that value is 14,842.3 millimeters per second. And that's a very large number, so we might be just better off converting that to meters per second by dividing that value by 1,000. And we get that the velocity of the fluid coming out of the needle is 14.8 meters per second. All right, so that does it for Vodcast number 15. Next time we'll continue on with section 5.2, where we'll talk about the conservation of, linear momentum and a moment of momentum equation. And then we'll talk about conservation of energy in section 5.3, and we will not do 5.4 for this class. So we have 2 more vodcasts for chapter 5. Your homework has been posted to the Moodle site, and we'll see you next time for 5.2.